Hi everybody, welcome back to Trigonometry. Today we're in section 5.2 and we're going to be verifying trigonometric identities. In this section I'll give you some strategies for verifying trig identities and we'll go over a few more algebra techniques. And then we will learn how to verify identities by working with the expression on one side of the equal mark and also how to verify identities by working with the expressions on both sides of the equal mark. So here we go. Now you know several identities already, so you know that an identity is an equation that is true for all values of the variable. To verify trigonometric identities means to prove that two expressions have the same value for all values of the variable, and that's why these problems are also called proofs. To prove or verify that a trig identity is true, we will use trigonometric identity substitutions and algebra, just like we did in section 5.1. Now it's important to keep in mind that trig identities look like equations, but they are not like normal equations that you solved in algebra. Usually when we solve an equation in algebra, there's only a limited amount of numbers that will make an equation true. And that kind of equation is called a conditional equation. And so with a conditional equation, we typically want to solve and find out what value of the variable makes the equation true. And you know how we do that. We add the same thing to both sides, or we divide both sides by the same thing. And we're allowed to do that with an equation because we're allowed to assume that the equal sign can be trusted. But when we verify identities, we're not trying to find what values make the equation true. Instead, we are trying to prove that the equation is true for all values of the variable. Now, logically, you can't prove that something is true by assuming it's true. So we can't use equation solving steps when we're verifying identities. Instead, we have to act as though we don't trust the equal sign. So what we'll do is we'll work with the expression on one side of the identity and transform it so that it looks like the expression on the other side. So, the first step in verifying an identity is to choose which side you want to transform. And it's usually easiest to transform the more complicated side so that it looks like the simpler side. So usually the more complicated side is the one we'll choose. Whichever side you choose to work with, copy that expression down on the left side of your proof and do not copy both sides of the identity. Only copy down the side that you're going to be working with. Then you'll use algebra and trig substitutions to transform that expression so that it's identical to the other expression on the other side of the identity. Now, if neither side looks more complicated than the other and you don't know which to choose, we can also choose to simplify both sides one at a time so that they're both identical to some third expression. And we will see an example like that later in the section. But whether you're planning to work with only one side or whether you're planning to work with both sides, either way, for each step you do, write the type of identity that you used or the type of algebra step that you did. And if you're going to use a trig substitution, you need to circle the expression that you'll be replacing. So you have to remember that when you're verifying trig identities, there's not a single number that's an answer like there is with a lot of the problems that we work. When you're verifying trig identities, your thought process is what's being graded. So for maximum points, it's important that you communicate your thought process throughout the proof by justifying each step. So again, if you make a trig substitution, circle what you'll be replacing and then state what kind of identity gives you permission to make that substitution. And if you perform an algebra step, state what you're doing. For example, if you reduce a fraction, just write reduce. Or if you distribute something, write distribute. It doesn't have to be fancy and there's no set vocabulary that you have to use, but just basically say what type of step you're doing. And you'll see in the examples that we do what I'm talking about. So here's our first strategy, using reciprocal and quotient identities. We can use the reciprocal and quotient identities to write everything in terms of sines and cosines and then reduce. We saw that a little bit already in our last section. And as we saw before, these identities can only be used within a single term. If you're going to use this strategy on a fraction that already contains terms, then you can't use these identities on the whole expression. Instead, what you'll have to do is create complex fractions. And now we're going to do two proofs that use this strategy, one that will be pretty straightforward and simple, and another one that will require us to simplify a complex fraction. So here's example 1, our very first proof together. It says verify that the following equation is an identity. And we have cotangent of x over cosine of x times cosecant of x equals 1. Now since this is our first one, I have some extra instructions for us here. It says start by copying the expression that you'll be transforming on the left side of the line. So we have to choose which side of the equation we want to work with. Do we want to work with this expression on the left, or do we want to work with the 1? You always want to choose to work with the more complicated expression, which is clearly the left side. So let's go ahead and copy down the left side of the equation, and notice that it says do not copy both sides of the identity. That's a big no-no, because we are only working on this expression, and we want to simplify this until we can show that it equals what we see on the right side of the equation we're trying to prove. So I'm not going to write equals 1 here. Now it says circle each trig substitution, and on the right side of the line that we have here, justify each step. Now since our strategy here is to write everything in terms of sine and cosine, you might already be looking at this and saying, I know that I could replace cotangent of x with cosine over sine, and that's a good thought. So since that's what we're going to be replacing, let's go ahead and circle that, and then on the next line, here's my fraction bar, let's rewrite cotangent of x as cosine of x over sine of x. Now the cosine of x times cosecant of x that's in the denominator, that's not changing on this step, so let's just copy that right where it is. Now what kind of identity did we use to change cotangent of x into cosine of x over sine of x? We used a quotient identity. So that's what you want to write over here on the right side. Now what's the next thing we could do here to simplify this expression? Well, you may notice that we have cosine of x in the top and in the bottom. So those will divide out, and since the entire top is now divided out, that leaves a 1 there. And over here on the right side, I'll write reduce because that's what we did. And now I'm going to rewrite what's left. You don't always have to do this, but sometimes it helps us to see more clearly if we get the things that have been crossed out of the way. So at this point, we're left with 1 over sine of x times cosecant of x. And always remember what you're aiming for. We are trying to simplify this so that it is a 1. And now at this point, you might notice that we have cosecant of x in the denominator, and you might say, well, we could restate that as sine of x in the top of the expression. So let's circle our cosecant of x, and let's go ahead and restate that as sine of x in the top, and this sine of x in the denominator is still going to be there. Now I need to write down what kind of identity I used to do that, and that would be a reciprocal identity. And now sine of x divided by itself reduces to 1. So I'm going to write again that I reduced, and then what's left of the expression is just a 1, and that matches what we have on the right side. So that's how we know we're finished. Now I promised you that we would do a proof together involving complex fractions, but before we do that, let's just practice the algebra technique of creating and simplifying complex fractions. So as you already know, if a fraction contains terms, we can't use the quotient identities or reciprocal identities on the whole expression. However, we can use these identities on individual terms, and that's going to create a complex fraction, which is just a fraction that's made out of fractions. And to simplify a complex fraction, what we'll do is multiply both the top and the bottom by the common denominator of the little denominators. And you'll see what I mean by that in example 2. And here we are. It says restate the expression using sine and cosine only. Simplify so that no complex fractions appear. and we have 1 over the quantity secant of alpha minus tangent of alpha. Now we know that secant of alpha is a term of the denominator because of the minus sign. And because secant of alpha is a term, we cannot use a reciprocal identity to restate secant of alpha in the denominator as cosine of alpha in the top. But what we can do is create a complex fraction. So we're still going to have 1 over, so I've copied that here, but now secant of alpha is going to be restated as 1 over cosine of alpha. And then we've got our minus sign. And let's go ahead and restate tangent of alpha as sine of alpha over cosine of alpha. Now to be consistent with what we did in example 1, we're going to write down the identities that we're using as we go along. What kind of identity lets me restate secant of alpha as 1 over cosine of alpha? That would be a reciprocal identity. And what kind of identity lets me restate tangent of alpha as sine of alpha over cosine of alpha? That would be a quotient identity. Okay, now this is a complex fraction. And like we said before, the way to simplify a complex fraction is to multiply the top and the entire bottom by the common denominator of the little denominators. By little denominators, I mean the denominators of the individual terms. And those are both cosine of alpha. So that tells us that we want to multiply every term in the top and every term in the bottom by cosine of alpha. So let's recopy here, and then we'll multiply every term in the top and every term in the bottom by cosine of alpha. Now this is allowed because as long as we multiply the same thing into the top and the bottom, we're essentially just multiplying by 1. So I'm going to write here that we multiplied by cosine of alpha over cosine of alpha. And now let's see what happens. In the top, 1 times cosine of alpha is cosine of alpha. In the bottom, we'll simplify 1 fraction at a time. So for this first fraction, we have cosine of alpha over cosine of alpha. Those are going to divide out. So let's write down reduce to show what we did here. And of course, that just leaves a 1 in the denominator. Then for the other fraction, we have cosine over cosine, which will also divide out. And that just leaves minus sine of alpha there. And so now we've got cosine of alpha divided by the quantity 1 minus sine of alpha. And so you can see that we satisfied the instructions because now it's in terms of sine and cosine only, and there's no complex fraction there. So this is a technique we can use whenever it's convenient for us. Now we're ready to tackle example 3, still using the strategy of writing everything in terms of sines and cosines. So it says verify that the following is an identity. And we have cotangent of x plus 1 all over cotangent of x minus 1. And that's supposed to be equal to cosine of x plus sine of x all over cosine of x minus sine of x. Now here I think that we don't see either side as necessarily being more complicated than the other one. So I'm going to choose to work with the left side. That's just a choice that I'm making. And you could also choose to work with the right side, but I think for us it will be more approachable if we choose to work with the left side. So I'm going to copy the left side of the equation on the left side of my proof. And the plan is to restate cotangent of x in terms of sines and cosines and keep reducing and working with this until it looks like the right side, and that's how we'll know we're finished. So now let's look at the expression we have here. We know that we have terms involved because we see the plus and the minus. So that tells us that we cannot restate cotangent of x as cosine of x in the top and sine of x in the bottom of the whole expression. But as we saw in example 2, we can restate this as a quotient within its own term. So for our first step, let's get a fraction bar here, and then let's circle both cotangent expressions. And each of these we're going to restate as cosine of x over sine of x, but within its own term. So this cotangent of x becomes cosine of x over sine of x, just like that. And then we have our plus 1. And then in the denominator, cotangent of x will be rewritten as cosine of x over sine of x, and then we have this minus 1 here. Okay, now what kind of identity did we use to make that change? That was a quotient identity. And now, of course, we just want to simplify the complex fraction. Look at both little denominators. They are both sine of x. So I know that I need to multiply every term in the top and every term in the bottom by sine of x. Now, just for clarity, I'm going to recopy this so that you can see what's happening in the next step. And we said multiply every term in the top by sine of x and every term in the bottom by sine of x. Okay, so that's done. Let's go ahead and write over here what we did. We multiplied top and bottom by sine of x. Now let's see what reducing we can do. I notice that here in the first term in the top, the sine of x's are going to cancel out. And also in the first term in the bottom, the sine of x's will cancel out. So we'll cross those out and then we'll just write reduce. And now let's collect what's left. Let's get our fraction bar. In the top of our simplified fraction, we'll have cosine of x, and then a plus sign, and then 1 sine of x is just sine of x. In the denominator, we'll have cosine of x, and then a minus sign, and then 1 sine of x is just sine of x there. And now if you compare what we ended up with the expression from the right side of our equation, you can see that they match exactly, so we know we're finished. Now let's look at strategy number 2, using Pythagorean identities to make substitutions. So I want you to watch for opportunities to substitute using Pythagorean identities, but you can't do that if you don't know the Pythagorean identities. So if you have not already memorized our 3 Pythagorean identities, please make sure and do that as soon as possible because it will make your verifying problems so much easier. Basically, anytime you see a squared function and a 1, that should be a clue for you to consider whether a Pythagorean substitution might be helpful. So here's example 4, and it says verify that the following is an identity. Tangent squared x times parentheses 1 plus cotangent squared x is supposed to be equal to 1 over 1 minus sine squared x. Now when I look at this equation, the left side of the equal mark looks more complicated to me than the right side because the left side involves 2 different functions. So I'm going to go ahead and copy that left side of the equation onto the left side of my proof. Now you might be wondering if we could distribute the tangent squared x here. We could do that and it would not be wrong. But in this example, I want us to focus on the strategy of making a Pythagorean substitution. So that's the direction we're going to go here. Now look inside the parentheses here and you see a 1 and a squared function. And that should always make you wonder if you could possibly replace these 2 terms with the other side of a Pythagorean identity. And if you've memorized your Pythagorean identities, you know that 1 plus cotangent squared x is equal to cosecant squared x. So I'm going to circle that parentheses there because I know that I'm going to replace what's inside the parentheses with cosecant squared x. So now on the next line, let's keep our tangent squared x and let's replace what we have circled here with cosecant squared x. And over here on the right side, I'm going to write down that I used a Pythagorean identity to make that substitution. Now, I even wrote down here exactly what identity was used, but on a test, I wouldn't even require you to write this because I can see here what you think the identity is. I just want you to tell me that you know that you're using a Pythagorean identity to do this. Now, this is good as far as it goes, but you can see that we're not there yet because this does not yet look like the right side. So now I'm going to use the strategy of writing everything in terms of sines and cosines. First, I'm going to circle my tangent squared x, and I know that tangent squared x can be replaced with sine squared x over cosine squared x, and we used a quotient identity to make that substitution. And then in the same step, I'm also going to circle the cosecant squared of x And I'm going to use a reciprocal identity to restate cosecant squared from the top as sine squared x in the bottom. And I'm going to write over here that I used a reciprocal identity as well. Okay, now you probably can see what needs to happen next. We have sine squared x in both the top and the bottom, so those divide out and it leaves a 1 in the top. And now over here on the right, I'm just going to state that I reduced there. And let me recopy now what we have. So we have 1 over cosine squared x. Now take a look at what we have here and compare it to what we want it to look like. You can see that we have cosine squared of x. We want it to say 1 minus sine squared of x. So we ask ourselves, is there an identity that links cosine squared x with sine squared x? And there is. That should make us think of our Pythagorean identity, sine squared x plus cosine squared x equals 1. And we know that if we take that identity and isolate cosine squared of x, the other side of the equal mark will have 1 minus sine squared of x. So now let's circle cosine squared x, and let's replace that with 1 minus sine squared x. And over here on the right, you want to state that you used a Pythagorean identity, and I've even written out here which one we used. Now as we go through this section, just keep in mind that all you would need to give on a test is just state that you used a Pythagorean identity. I'm writing out the identity itself for your convenience, but you would not be required to do that on a quiz or a test. And now, because we have reached an expression that is equal to the other side of the identity we're trying to prove, we can say that our work is done. We proved the identity is true. Now let's look at strategy number 3. Perform any operations in the expression that you want to transform. If the expression that you're working on contains distributing, or if there are two factors that can be multiplied together with the FOIL method, or if you see factoring that can be done, then go ahead and do that. If there is addition or subtraction in your expression, then get a common denominator and write the result as one fraction over a single denominator. And even though you may not see it when you start, very often doing that operation will get you a step closer to the result you're trying to achieve. So here is example 5, and it says verify that the following is an identity. Cotangent theta plus 1 is equal to cosecant theta times parentheses cosine of theta plus sine of theta. Now I think we would all agree that the right side is a little more complicated than the left side, so it's the right side that I'm going to copy down into my proof. Now the very first thing I see when I look at this expression is that I could distribute that cosecant of theta. So let's do that first. We'll have cosecant of theta times cosine of theta, then we'll have a plus sign, and then we'll have cosecant of theta times sine of theta. And I'm going to write over here distribute because that's what we did. Now notice that we're already one step closer to the result we're trying to get to because this left side has two terms and no parentheses. And what we have here already has two terms and no parentheses. So we've made a step in the right direction, and that's great. Now I notice that both terms contain cosecant of theta. So we can use one of our reciprocal identities to write each of these as sine of theta in the denominator. Let's go ahead and circle both cosecant functions. And now for the first term, we'll keep our cosine of theta in the top, and then in the denominator we'll have sine of theta. Because we know that if we have cosecant of theta in the top, we can restate that as sine of theta in the bottom. Then for our second term, we'll keep this sine of theta in the top of the term, and we'll restate this cosecant of theta as sine of theta in the denominator. Okay, now over here on the right side, what kind of identity did we use to do this? That was a reciprocal identity. And now every time you finish a step, look at what you've got and look at what you're trying to get to. And you probably can see now how we can get there. So in this first term, we have cosine of theta over sine of theta. I'm going to go ahead and circle that, and we know that cosine over sine is equal to cotangent. So I'm going to replace what I circled with cotangent of theta, and now over here on the right side, I'm going to write that we used a quotient identity to do that. And now for this second term, sine of theta divided by itself is 1. So we'll have plus 1 in our result, and I'm going to write over here that I reduced. And now look, the cotangent of theta plus 1 that we got here is identical to the other side of our equation, and so this identity is proved. And here's example 6. Verify that the following is an identity. Cotangent of theta plus tangent of theta equals secant of theta times cosecant of theta. Now, in this case, both sides contain two functions, so it may not be clear to you which is the more complicated. But I want you to notice that on the left side we have a plus sign. So that's an operation that we can do. So I'm going to suggest that we start off by working on the left side. And let's see if we can transform this into secant of theta times cosecant of theta. So we see the plus sign here, and we want to do the addition. But we know that whenever we add trig functions together, it's essentially a matter of getting a common denominator. So we need some denominators here. Let's replace each of these functions with their quotient identity. So I'm going to circle both of them and then replace them one at a time. Cotangent of theta is cosine of theta over sine of theta. And then we'll have our plus sign. And then tangent of theta is sine of theta over cosine of theta. And let me write over here that I used a quotient identity to do that. Now, in order to accomplish the addition, I'm going to have to get a common denominator. So let me recopy this just so you can see what's going on. And I've spread the terms apart a little bit so I have room to write. Now, this denominator is sine of theta, and the other denominator is cosine of theta. So this first denominator needs a cosine of theta in it. I'm going to multiply this first fraction by cosine of theta over cosine of theta. Now the second fraction has a cosine but not a sine, so I'm going to multiply this second fraction by sine of theta over sine of theta. Over here on the right side, I'm just going to justify my thought process by writing out that I got a common denominator. Okay, now you can see that both denominators are sine of theta times cosine of theta. For our next line, let's go ahead and write a fraction bar and put that common denominator under the fraction bar. And now the new top will be cosine theta times cosine theta, which is cosine squared theta, plus sine of theta times sine of theta, which is sine squared theta. Over here on the right, I just want to explain what I did in that step, so I just wrote combine into one fraction. I don't want you to feel like there's any one set of phrases that you can write over here on the right side. You're basically describing or explaining what's happening on the left side, and that can be in your own words. So, for example, I wrote combine into one fraction, but someone else might just write combine, or they might write restate as one fraction. See, there's no magic phrase that makes it correct or incorrect. It just needs to be an accurate explanation of what happened on the left side. Now let's see if we can figure out what we have to do next. Whenever you're wondering what you have to do next, you look at what you've got, and we've got cosine squared theta plus sine squared theta, all over sine theta times cosine theta, and you compare that to what you're trying to get to, which for us here is secant theta times cosecant theta. And so you can see that we've got to somehow eliminate the denominator from this expression. And it might not be obvious yet how we're going to do that, but when I look at the top of this fraction, I see two squared functions. And it kind of makes me think of one of our Pythagorean identities. We have cosine squared theta plus sine squared theta. We know that that is equal to 1. We know sine squared theta plus cosine squared theta is 1. So I'm going to circle that, and on the next line replace that with a 1. Now I've still got my sine theta and cosine theta in the bottom, and over here on the right, I want to state that I used a Pythagorean identity to make that change. Now look again at what we have, and compare that to what we want. And I think this time you probably can see what our last move needs to be. We have sine of theta in this denominator, and we want to end up with cosecant of theta in the top. Well, we know how to do that using a reciprocal identity. And we have cosine of theta in the denominator, and we want to end up with secant of theta in the top. And that also can be done with a reciprocal identity. So to finish this up, we're going to circle our sine of theta in the denominator here, and we're going to restate that as cosecant of theta in the top of our expression. And we're also going to circle our cosine of theta and restate that as secant of theta in the top. And let's write down that we used reciprocal identities to do both of those things. And now the order of the factors is different, but we know that order does not change the result of multiplication. So the result that I have here is identical to the other side of my equation, and therefore this identity is proved. And now strategy number 4, which is to split a fraction into 2 terms. So if you have a fraction and there are multiple terms in the top but only one term in the bottom, try splitting the expression into separate terms. Now you already know this from section 5.1, but each term will have the same denominator after the split as it did before the split, and then you can reduce each fraction separately after you split. And also just keep in mind that denominators cannot be split this way. And so to practice that strategy, here is example 7. And it says verify that the following is an identity. We have sine squared theta over cosine of theta, and that's supposed to be equal to secant of theta minus cosine of theta. Now you actually could prove this identity by transforming either expression, but because I want to practice splitting the fraction with you, I'm going to work with the left side of the equation. So let's copy down the left side here. And now you know when we're trying to decide what move to make next, we look at what we've got and we compare that to what we want it to look like. And this expression that we're aiming for has 2 terms. So we would like to create something with 2 terms over here. So is there a way to change this sine squared theta into something that has 2 terms? Well, of course, it's a squared function, so that makes us think of our Pythagorean identities. And we know that sine squared theta plus cosine squared theta is 1. And that means that 1 minus cosine squared theta is sine squared theta. So let's circle our sine squared theta. And on the next line, let's replace sine squared theta with 1 minus cosine squared theta. Then the denominator is still cosine theta. And over here on the right side, let's write down what kind of identity we used to make that change. And of course, we used a Pythagorean identity to do that. And now you see we have what we wanted, which was 2 terms in the top. So now we'll split this into 2 separate fractions, and each one will have cosine theta as its denominator. So my first one will be 1 over cosine theta, and then we'll have a minus sign, and then the next term will be cosine squared theta over cosine theta. Over here on the right, I'm just going to explain what I did, and that was to split into terms. Or you could say split the fraction, or you could say separate terms, whatever. Just explain what you did here. Now look at what we've got, and look at what we're trying to get to. Now when you look at the first term, do you see a way to get from this first term to the first term here? And of course you do. You know that cosine in the bottom of an expression can be restated as secant in the top. So let's circle cosine here in the denominator and restate that as secant of theta in the top. And over here on the right, I'm going to put that I used a reciprocal identity to do that. And then for the second term here, we notice that the cosine theta in the denominator will cancel one of the cosine factors in the top. And it's also going to leave a cosine factor in the top. So now I'm going to have minus cosine theta. And look, that is an exact match for the other side of our equation. All we need to do now is write down that what we did here was reduce, and that identity is proved. And here's example 8. We want to verify that tangent of x minus cotangent of x all over sine of x times cosine of x is equal to secant squared x minus cosecant squared x. Again, there are a couple of different ways you could go here, but I want to practice splitting the fraction. So I'm going to choose to work with the left side of this equation because I notice that I've got two terms in the top here and I can split that into two pieces. So let's copy down the left side of our equation here. And now for our first step, let's just split that into two terms. Each term will have sine of x times cosine of x in its denominator. First we'll have tangent x over sine of x times cosine of x, and then a minus sign, and then we'll have cotangent of x over sine of x times cosine of x. And over here I want to explain that I split into terms, or you could say split the fraction, whatever you want to say. Okay, now I notice that in each term I have a tangent or a cotangent, and I know that I can use quotient identities to write those in terms of sines and cosines. So in the first term, let's circle the tangent of x and restate that as sine of x over cosine of x. Now in the denominator, I'm still going to have sine of x times cosine of x. Then we've got our minus sign. And then for the second fraction, let's circle cotangent of x, and let's restate that as cosine of x over sine of x. And in that denominator, we've also still got sine of x times cosine of x. Over here on the right side, to explain, let's write quotient identity, because that's the kind of identity we used on both of those terms. Now, is there any reducing we can do? Of course, in the first fraction, we see that we have sine of x in both top and bottom, and so dividing those out leaves a 1 in the top. And for the second fraction, we see that we have cosine of x in both top and bottom, and that also leaves a 1 in the top there. And over here on the right, let's state reduce to explain what we did here. Now, just to clean this up a little bit so we can see it better, I'm going to rewrite this as 1 over cosine squared x minus 1 over sine squared x. And now let's look at what we've got, and let's look at what we're aiming for. You can see that the first term in our work here has cosine squared x, but we are aiming for it to say secant squared x. And of course, all we need to do to get that result is use a reciprocal identity. So let's circle our cosine squared of x, and let's restate cosine squared in the denominator as secant squared x in the top. And then we've got a minus sign here. And let's do the same thing for this second fraction. Sine squared of x in the denominator can be restated as cosecant squared x in the top. And of course, we used reciprocal identities to do both of those. And now notice that what we have here is identical to what we were aiming for, and so we can say that identity is proved. Okay, now before we get our next strategy, I want us to look at another algebra technique together. Binomials that contain trig functions can be multiplied just the same as any other binomials. All we have to do is use the FOIL method and combine like terms at the end. So let's practice that in example 9. The instructions say perform the operation and simplify to as few terms as possible. In part A, we have sine of alpha minus cosine of alpha in parentheses all squared. So in order to make it easier for us to see how to use the FOIL method, let's eliminate the exponent and write this as sine of alpha minus cosine of alpha times itself. Now we can more clearly see how to use the FOIL method. So we know that FOIL is first, outer, inner, last. So first times first would be sine of alpha times itself, so that would be sine squared alpha. Outer times outer would be sine of alpha times negative cosine of alpha. So that's what I'll write here. For the inner times inner term, we'll have minus cosine alpha times sine alpha. But in order to keep my like terms looking alike, I'm going to keep the sines and cosines in the same order every time. So I'm going to write minus sine of alpha times cosine of alpha. And then for last times last, negative times negative will make positive cosine squared of alpha. Okay, now let's see what we can do to have fewer terms in our answer. First, I notice that we have two squared functions. We have sine squared alpha plus cosine squared alpha. And of course, we know that one of our Pythagorean identities says sine squared alpha plus cosine squared alpha equals 1. So let's circle those and replace those two terms with a 1. And then let's combine these two like terms. So we have minus 1 sine alpha cosine alpha minus another 1 sine alpha cosine alpha. Together they make minus 2 sine alpha cosine alpha. And now let's look at part B. So here we have 1 plus sine of theta times 1 minus sine of theta. This is what's called a sum and difference of the same two terms. But we still will multiply these two factors together using the FOIL method. So here we go. First times first is going to be 1 times 1, so that's 1. Outer times outer is going to be minus 1 sine theta. Inner times inner is going to be plus 1 sine theta. And then last times last is going to be minus sine squared theta. Now let's think about combining our like terms here. In the middle we have minus 1 sine theta plus 1 sine theta. We know that those two would add up to 0. So then we would have 1 minus sine squared theta. And if we're trying to get as few terms as possible, like they asked in the instructions, we know there's one more thing we can do here. This should remind us of our Pythagorean identity, sine squared theta plus cosine squared theta equals 1. If you rearrange the terms so that one side says 1 minus sine squared theta, the other side will say cosine squared theta. As we know, we remember that from section 5.1. And so multiplying these two factors together all boil down to cosine squared theta. So now here is strategy number 5, and that is to multiply the top and bottom of a quotient by the conjugate to get a squared function. So we need to talk about what a conjugate is. If you have 1 plus or 1 minus a trig function to the first power, for example, 1 plus sine of theta, or 1 minus cosine of theta. As long as it's two terms, you've got 1 plus or 1 minus, and then a trig function that's to the first power, then you can multiply the top and bottom of that expression by the conjugate of that expression to get a squared function. And now a conjugate is the same two terms but with a different sign in between them. So for example, the conjugate of 1 plus sine theta would be 1 minus sine theta. And the conjugate of 1 minus cosine theta would be 1 plus cosine theta. Now what's the benefit of multiplying conjugates together? The benefit is that after you FOIL out the conjugates, you'll have a squared function and you'll be able to make a Pythagorean substitution. So let's look at example 10 together. Verify that the following is an identity. Cosine of theta over 1 minus sine of theta is supposed to be equal to 1 plus sine of theta all over cosine of theta. Now if you ask yourself which of these two sides is more complicated than the other, the answer is they're really about the same. So I'm going to choose to work with the expression on the left side of the equal mark. You could just as easily apply the same method we're going to use to the right side of the equal mark. But let's just go ahead and copy down cosine theta over 1 minus sine theta. Now I want you to look at this denominator for a second. I know that it might look almost like part of a Pythagorean identity. It's 1 minus sine of theta. All of our Pythagorean identities involve squared functions. So if this said 1 minus sine squared theta, we'd be in business. We could make a Pythagorean substitution right there and be done. But it's not that easy because this is not part of a Pythagorean identity because it does not have the squared function. In order to fix that, we need to multiply this by its conjugate. So I'm going to recopy my expression here, and now I'm going to multiply both the bottom and the top by the conjugate of these two terms, which is going to be 1 plus the sine of theta. Do it to the bottom and the top. Over here, let's just explain that we're multiplying by 1 plus sine of theta over itself. And for a test, that would be good enough for you to state that. But for your notes, I'm going to add that we're doing that because it's the conjugate of 1 minus sine theta. Now, in the top, you see that you could distribute this cosine of theta if you wanted to, but I'm going to say hold off on that. There's really no need to do that, because if you distribute that cosine of theta, it will be harder later to reduce if we need to. So just leave this undistributed. We'll copy it exactly as is. But in the denominator, that's where we're trying to make something happen. So we are going to use the FOIL method on this denominator right here. So first times first would be 1. And then when you look at outer plus inner, you can see that would add up to 0 because it would be sine theta minus sine theta. And by the way, you can always count on the outer plus inner adding up to 0 whenever you multiply conjugates together. Then last times last would be minus sine squared theta. Over here on the right, I'm going to say that I used the FOIL method. And then in the denominator, I see that I have 1 minus sine squared theta, and that is part of a Pythagorean identity. We know that 1 minus sine squared theta is equivalent to cosine squared theta. So let's circle that, and then when we recopy our expression, we'll keep the top the same, but we will replace 1 minus sine squared theta with cosine squared theta. Over here on the right, we want to put that we used a Pythagorean identity. And now notice that we have cosine theta in the top and cosine squared theta in the bottom. So this cosine in the top will cancel one of our cosines in the bottom, and we'll be left with 1 plus sine theta in the top and cosine theta in the denominator. I'm going to write over here on the right side that we reduced. And now look at what we ended up with compared with the right side of the equation we started with, and you can see they're identical, and so that means we're finished with that proof. Now here's another algebra technique. Sometimes expressions will need to be factored in order to see what cancels out. Trig expressions will factor with the same rules that you learned in algebra. So here in example 11, we're going to practice just a little bit of factoring. It says factor each trigonometric expression. In part A, we have sine squared theta minus 1. Now, if you remember from algebra how to factor a difference of squares, this should look familiar to you. A difference of squares is a square minus another square. Anytime you need to factor a difference of squares, it's going to factor into two binomials. So you'll have two empty sets of parentheses there. Then you need to ask yourself, what times itself could produce sine squared theta? Well, of course, sine of theta times sine of theta made sine squared theta. All right, then for your sines, you know that last times last is going to have to make a negative number. So that means that these two sines are going to have to be different. And then you have to ask yourself, what times itself produced this last term here? And so that would have to be a 1 for us. So we'll have 1 here and 1 here. Now, to check your work, to make sure that your factoring is correct, you want to mentally go back through the FOIL method and make sure that you get this as a result. So let's do it. First times first would make sine squared theta. That's what we have here. Outer plus inner is going to be the same two terms but different signs. So they're going to add up to 0, and that's why you don't see them here. And then last times last is going to make negative 1. So we have minus 1 here. So we're sure now that this factoring is correct. And then let's look at part B together. So here we have a trinomial. And you remember from algebra that when you want to factor a trinomial, it's going to factor into two binomials. So let's start with our two empty sets of parentheses, and let's ask ourselves what times what would make 2 sine squared theta. Well, the only way to get 2 is to have 2 times 1. And the only way to break down sine squared theta is sine of theta times itself. So if we want to separate this into 2 factors, we could have 2 sine of theta times 1 sine of theta. Together, those multiply to 2 sine squared theta. All right, now let's think about the signs that go in our parentheses. Last times last made a positive number. Now, don't worry about the 1 at this moment because all we're thinking about is this plus sign right here. The only way for last times last to produce a positive number here is if these 2 signs that go right here are the same. Negative times negative would make a positive last term, and positive times positive would make a positive last term. So how do we decide which one to use? Well, the sign of the middle term will tell us. So the middle term is positive, so that means that we're going to want 2 plus signs there. That's going to give us a positive middle term and also a positive last term. And now we can think about the 1. So we ask ourselves what times what would produce 1? And of course that's just 1 times 1. Now we know that first times first produces 2 sine squared theta, and we know that last times last produces plus 1. So those 2 terms are fine, but we do need to check that outer plus inner would add up to 3 sine of theta. So outer times outer would be 2 sine of theta. Inner times inner would be 1 sine of theta. 2 sine theta plus 1 sine theta is 3 sine theta. And so that's all we need to know that this factoring is correct for this trinomial. And here's strategy number 6, which is our last strategy to look at, and that is to simplify both sides to some third expression. So if both sides are fairly complicated, you can choose to simplify each side separately and show that both sides are equal to some third expression. And this works because 2 things that are equal to the same thing are equal to each other. So here is example 12, and it says verify that the following is an identity. We have secant of alpha plus tangent of alpha all over secant of alpha minus tangent of alpha, and that's supposed to be equal to 1 plus 2 sine alpha plus sine squared alpha all over cosine squared alpha. Now if you're like me, you can't imagine simplifying what we see on the left side here and ending up with what we see on the right, because that doesn't look simple at all. And the same thing goes for the right. We're not going to simplify this expression on the right and end up with what we see on the left. So this is a time when we can think about simplifying both of them to some third expression, and if we can get both of them to simplify to the same thing, then we can say the identity is proved. So now we've got to work with both sides, but we're going to take one at a time. And so let's start with the expression on the left side of the equation. And here we see that we have terms. So remember our first strategy of writing things in terms of sines and cosines, but when we have terms, we have to create a complex fraction. So we actually are going to apply our reciprocal identities to both secant expressions and our quotient identity to both tangent expressions. So let's go ahead and circle all 4 of these. And now we will rewrite each function. So secant of alpha can be restated as 1 over cosine of alpha, and then we have our plus sign. Tangent of alpha can be restated as sine of alpha over cosine of alpha. Then in the denominator, again, secant of alpha can be restated as 1 over cosine. Then we have a minus. And then tangent of alpha can be restated as sine of alpha over cosine of alpha. Over here on the right, let's give our reason as reciprocal identities and quotient identities. Now, remember how to simplify a complex fraction. We want to multiply the top and the bottom by the common denominator of all the little denominators. Now, every one of the little denominators is cosine. So that means we will want to multiply the top and the bottom of our whole expression by cosine alpha. So I'm going to recopy here just to keep things clean. You probably would not recopy on your own paper. And now I'm going to multiply through the top by cosine of alpha, and I'm going to multiply through the bottom by cosine of alpha. And over here for our explanation, let's just say that we multiplied by cosine alpha over itself. And now let's simplify each term. You can see here in the top left fraction, the cosine alphas cancel out. In the top right, they cancel out. Bottom left and bottom right. So we've canceled cosine alpha over itself in every term. So over here in the right column, let's explain that we reduced there. And that leaves us with 1 plus sine of alpha all over 1 minus sine of alpha. Now, as you can see, we've ended up with an expression that is much simpler than the right side of the equation we're trying to prove. So this is a good place to stop and see if we can now work on the right side and get it to look the same as what we've ended up with on the left side. So now over here, I'm going to recopy the right side of the equation. And if we look at the top here, we notice that this is a trinomial. And that means that there is a possibility that this could be factored. So let's go ahead and circle this top here and see if we can factor it. Now, because it's a trinomial, it's going to break down into two binomials. And what we're trying to do when we factor is reverse the FOIL process. So let's break it down. The first term here is a 1. So that's going to break down into 1 times 1 in our factoring. The sign of the last term is positive. That tells us that the signs in our factoring have to both be the same, and they have to be the same as whatever the middle term is. So they both will have to be plus. Now, last times last is sine squared alpha, so that's going to have to be sine of alpha times sine of alpha. And let's write down over here on the right side that we factored. Now look at your denominator. So we have cosine squared alpha in the denominator. If we were to copy that here, we'd be stuck because we would not be able to do any simplifying. So there's got to be something that we can replace cosine squared alpha with that will allow us to do some simplifying. And if you look back at the expression that we're aiming for, you can see that we have 1 minus sine alpha in the denominator. So we have to ask ourselves, do we have a way to connect sine of alpha with cosine squared of alpha? And the answer is yes. We have a Pythagorean identity that says sine squared alpha plus cosine squared alpha is 1. Now what we have here is just cosine squared alpha. So if you rearrange the terms of that Pythagorean identity, you'll find that cosine squared alpha is equal to 1 minus sine squared alpha. So I've circled my cosine squared alpha here, and I've replaced it with 1 minus sine squared alpha. And over here on the right, let's say that we used a Pythagorean identity. Now, if you look at this, you'll notice that it's a difference of squares. 1 is a square because it's 1 times 1. Sine squared alpha is obviously a square. So we have square minus square. So we're going to be able to factor this as a difference of squares. So now recopy your expression from the top, 1 plus sine alpha times 1 plus sine alpha. And now in the bottom, let's factor that difference of squares. So the first term here is a 1. That means first times first has to be 1. That must be 1 times 1. We know when we factor a difference of squares, the signs in the factoring have to be opposites. So I need 1 plus and 1 minus. And then sine squared alpha is going to break down into sine of alpha times sine of alpha. Over here on the right side, let's note that we factored that difference of squares. And now I'm sure that you see what to do next. We have a 1 plus sine alpha in both top and bottom, so those are going to divide out. Let's write over here that we reduced. And then what we're left with is just this, 1 plus sine alpha over 1 minus sine alpha. And that's the same simplified expression that we got when we worked on the left side. So now, since both expressions simplified to the same thing, we can say that they're equal to each other, so the identity is proved. Now, we've covered a lot of strategies in this section, so I just want to recap here quickly for you so you'll know what all tools you have available to you. So the first strategy we talked about was to use reciprocal and quotient identities to write everything in terms of sines and cosines. But you know that if your expression contains terms, then you can only use those identities to create a complex fraction and then you have to simplify the complex fraction. Our second strategy that we looked at was to make substitutions involving Pythagorean identities. And you know that you're not going to recognize when you can do that if you don't have the Pythagorean identities memorized. So you really need to have those memorized and firmly in your mind so that you can see when you have an opportunity to use them. A clue for you is that anytime you see a 1 in a squared function, you should think about whether a Pythagorean substitution is possible. Our third strategy was that if the expression you want to transform has operations, then you need to perform those operations. If there's anything you can do like distributing or using the FOIL method or factoring, then you want to go ahead and do those things. If there's addition or subtraction that can be done, then you'll just find a common denominator and combine the two expressions into one fraction with a common denominator. Strategy number 4 was that if we have a fraction that has terms in the top, we can split that into two separate terms and then simplify each one separately. Strategy number 5 was that if we have 1 plus or minus a first power trig function, then we can multiply top and bottom by the conjugate, and then after we use the FOIL method to multiply those two conjugates together, we'll be able to make a Pythagorean substitution. And then strategy number 6, if both sides are complicated, then you can simplify each one separately to some third expression. So we've done examples where we used each one of those things. And I'm sure that you noticed along the way that sometimes I chose to use one strategy when I could have used another strategy. There's very often more than one correct way to do these proofs. One person might choose to start by making a Pythagorean substitution. Another person might choose to start by writing everything in terms of sines and cosines. There's not one correct way. It's all about your thought process. So that's why it's so important for you to practice writing your own proofs. If you're reading proofs that somebody else wrote, you might understand them, but that's not the same skill as being able to look at an equation and decide which method would be the best for you. So please go in Canvas, work lots of practice problems, because you know my lab is not going to be able to tell you if your thought process is correct on these proofs. My lab is horrible for practicing proofs, but what you need to do is use the practice problems that are provided in Canvas, compare your answers to my answers, and if you have any questions, ask me if you're in my traditional class or ask your instructor if you're taking the class online. We would be glad to give you some feedback on your proofs so that you can get maximum points on your quizzes and tests. All right, you guys, I'll see you next time in section 5.3 for more identities. Bye-bye now.